Hello everybody. Today we are going to be reviewing limits and continuity on our journey to begin calculus. So let's start off first with, well, what is a limit? So limit notation is limit as x approaches c of some function of x. So what we mean here by this notation is, say we have a function. Let's say the function f of x equals x squared. So that's going to look like a parabola, something like this. Well, say we want to take the limit as x approaches 3 of this function x squared. So f of x would be x squared. So what we're looking for here is 1, 2, 3. We want to see here, well, what is, as x gets closer and closer to 3, as this x value gets super close to 3, what is this f of x value going to get super close to? So if we zoom in here on the curve, so this is going to be, we'll say, here is x equals 3, here is x equals 2.9. We want to see as x gets closer and closer and closer to 3, what value is f of x going to approach. And this is a simple one. Here we can just plug in the number x equals 3, and this is quite intuitive because you see basically when x is 3, you can just plug it in and you can get, well, let's see, x squared, so you plug in 3, so 3 squared, that's just going to be 9. And now it makes sense here, right? Because you have, as x gets super close to 3 on the parabola, you know that f of x at 3 is going to be 9, and that makes sense. But it gets more complicated for functions that are not continuous. And there are 4 main types of discontinuity. The first one being a removable discontinuity. So basically what a removable discontinuity is, let's say we have the function y equals x squared over x. Well, you might say, okay, let's just simplify that to y equals x. That's the same thing, right? Well, not exactly. So let's graph each of them. Let's first start with y equals x, because we all know what that looks like. That's just going to be a line with a slope 1 through the origin. Now, with y equals x squared over x, we have to be careful. So we can make this x squared over x equal to x. But since x is in the denominator at some point, we have to say that x cannot equal 0. So therefore, we are going to put something called a hole at 0. We can just denote it by an open circle. The rest of the line will be the same, but there will be a hole at x equals 0. So we can write this function as y equals x, but x cannot equal 0. The second type of discontinuity is called an infinite discontinuity. Infinite discontinuity. So an example of this is the function y equals 1 over x. And if we were to graph this quickly, we would get something that looks like this. And you can see here that this value is going all the way down to negative infinity when x is just barely less than 0. But then once x passes 0 and it starts to get positive, it's all the way up at positive infinity. So since it jumps from negative infinity all the way up to positive infinity. This is what we call an infinite discontinuity. Now something similar to that is called a jump discontinuity. It's essentially the same as an infinite discontinuity. However, a jump discontinuity is over a finite region. So let's say we have a piecewise function from x from 0 to 2. We have f of x equals x. And from 2 all the way, or we'll just say from 2 to 4, we have f of x equals x plus 1. Well, here, if we were to graph this, so we have 1, 2, 3, 4. So from x goes from 0 to 2, we have f of x equals x. So that's just going to be a line that goes from 0, 0 to 2, 2 from there. And we're going to draw a closed circle there because it's inclusive of 2. Now for the f of x equals x plus 1, it's going to go from 2 to 4. It's not going to be inclusive of 2. So we're going to draw an open circle where it touches at 2. So at 2, f of x plus 1 is going to be 2 plus 1 is 3. So we can draw an open circle up there, and then we know it's going to continue in the same direction as this, the same slope, but they're going to jump right here at x equals 2. Hence why it's called a jump discontinuity. And the final type of discontinuity is the least common one that you'll see, and it's called an oscillating discontinuity. The most famous example of this is the graph y equals sine of 1 over x, and it's called the topologist's sine curve. If we were to graph this, I'll graph it from right to left here to show you the idea of what's happening here. So as sine gets very close, as it's getting closer to 1 or closer to 0, the frequency of the wave starts to increase, and when it gets super close to 0, basically rapidly increases and goes up and down and up and down and up and down so quickly that we call it an oscillating discontinuity. So those are the 4 main types of discontinuity, and these are all very important when it comes to understanding what a limit is. So now to actually define a limit, well, a limit exists, we'll say limit as x approaches c of f of x it will exist if the limit as x approaches c, and this minus means from the left, so as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x. And let's take the example of a jump discontinuity. So if we look at the jump discontinuity example that we had before, I'll just quickly sketch it. So it was the y equals x, and the y equals x plus 1. Well, if we look at we'll see here, we went from 0 to 2 for this, so this is x equals 2. If we take the limit, if we want to look at if the limit as x approaches 2 of f of x, we'll just say f of x here because the function changes. does it exist? Well, it will exist if the limit as we approach 2 from the left and the limit as we approach 2 from the right are the same. And if we just look here, we can see, well, let's see, as we're getting very close to 2 from the left, we're coming along this y equals x curve. But when we're coming along this, when we're getting close to it from the right, well, we're coming along this y equals x plus 1 curve. And you can see that these 2 points are not going to be the same when you get very, very close to 2. Therefore, the limit at x equals 2 here does not exist. And in general, limits do not exist at points of discontinuity. So let's look at an example. Let's look at the limit as x approaches 2 of the function 2x. So here we are able to just plug this value in. And the reason, so we can plug in x equals 2. So we can get 2 times 2 is 4. The reason we can do this is because this function is continuous everywhere. So if we look at this, it's just a straight line, goes through the origin. It should be straight, it's a little curved. It's a straight line that goes through the origin and has a slope of 2. And we can see here clearly that there are no types of discontinuity. There's no removable discontinuity, no infinite discontinuity, no jump discontinuity, or oscillating discontinuity. So we can just simply plug in this value of 2, and if we plug that in, we get that at that point, f of x is going to be 4. So now let's look at a more interesting example. Let's examine the function y equals this thing. What does that mean? Well, these brackets with only the thing going in on the bottom, this is called the floor function. And essentially what the floor function is, so I'll draw, we have 1 there, 2, 3, that's not very evenly spaced, 3. So if we have that, what the floor function is going to look like is, it is going to be a step function, and it is going to round down to the nearest integer for every value of x. So for y, so say that x equals 0.5. We're going to round that, or we truncate, essentially. We don't even round down, we truncate to the integer that is lower. So let's say we have x, if we have x equals 2.1. If we truncate this decimal, we're just going to get 2. And if we look at the graph of this function, so we're going to then have a step here, should be a little straighter, so that's going to be at 1, that's going to be at 2. We're going to have a step here. This part, the part on the left here, is going to be filled in because for the value of x equals 2, that is going to just be at that integer that we are going to, at that value we are looking for. So here at x equals 2, that is going to be at that value we are already looking for, therefore it's just going to be a point there. Now if we're, say, very, 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 very close to 3 here, say 2.9999, well, remember we're just truncating this essentially. So we have to have a hole here, and it'll go all the way back down to what 2 is. And that's why we have the y value of 2 here for anything all the way up to like 2.999. All right. And one important limit to memorize for now, you will be able to evaluate it quite easily once you finish learning everything about derivatives. But for now, just remember that the limit as x approaches 0 of sine of x over x is equal to 1. And let's do a few examples of limits involving infinity. Alright, so let's start off with the limit as x approaches 2 from the left of 1 over x minus 2. Alright, let's first graph this. And obviously for quite a few graphs, you always know how to graph. Say you have the function y equals e to the sine of arctangent of x squared plus 1 over x. You won't just be able to graph that off the top of your head. But for something like this, something simple, the graph of 1 over x minus 2, you can just graph that. You know it's going to be 1 over x, but it's going to be shifted to the right 2. 1, 2. And we know that the graph of 1 over x is going to have an asymptote originally at x equals 0. Now it's going to be at x equals 2 because that's when the denominator is 0. So the graph of the function is going to look something like this. So let's look at it graphically, and then let's look at it analytically. So first graphically, well, if x is going to be approaching 2 from the left, well, let's look at the left here. As x is approaching 2 from the left, it seems that this is going down, 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 all the way to negative infinity. So graphically, we can say that this is negative infinity. Now let's check analytically. Well, how would we do this analytically? Well, how about we take a value of x that is very, very close to 2, but just slightly lower than it. Let's use the value x equals 1.9999. Well, if we plug this into our function, we get 1 over 1.9999 minus 2. If we evaluate this, or if we simplify this, we get 1 over 0.0001, and then that's going to be, what is that, 10,000, 1,000? It's going to be a lot of zeros. Now, if we make this number even closer to 2, say 1.999999999, this number is going to get even closer to 0, and therefore this number is going to get even bigger. So we can see that as we get infinitely close to 2, this number gets infinitely small, and therefore this number gets infinitely big. So that means this limit would still be approaching, sorry, this number should be negative, so this will be approaching negative infinity. This number is negative because this number is going to be slightly lower than this number. Now, what if we want to look at the limit as it approaches it from the right? Well, once again, graphically, we can just look at it here. See, from the right, it looks like it's going all the way up to positive infinity, so we can quickly verify that by doing it analytically. Let's choose a number x equals 2.00001. If we now do this, if we do put this in 0.00001 minus 2, we get 1 over 0.00001, and then that's going to be a big number. And we can see that as this gets closer to 2, that denominator is going to get even smaller. It's going to be positive though, and 1 divided by an infinitely small positive number is going to be infinity. So therefore we can say that limit will be equivalent to infinity. Okay. So we just looked at the limits from both the right and the left of this function. What if we want to just evaluate the limit in general? We don't want to choose a sign. Well, if you recall from earlier, this is actually an example of an infinite discontinuity, and therefore, since this is the point a point of discontinuity on this graph, x equals 2, this limit will not exist. And we had just evaluated the limit as it approaches from the left to equal negative infinity, and the limit as it approaches from the right to be positive infinity. We also said before that the limit as x approaches a number c will only exist if the limit approaching from the left and the limit approaching from the right are equal. And since they're not equal here, we can say that this limit does not exist. And then limits actually, you can have a limit of, as x approaches, it doesn't have to be a finite number, it can also be, say, infinity. Say we have the limit as x approaches infinity of the same function. Well, let's see, x is approaching infinity, so x is going all the way over here. Where is y getting close to? Y is getting super close to what? Well, it's getting just about touching the x-axis, so y is getting very close to 0. So we can say that that's 0. We can also say that because if we were to look at this, we say we plug in infinity on the bottom. Infinity minus 2 is still going to be infinity, and 1 divided by infinity is 0, because 1 is a finite, any finite number divided by infinity is going to be 0. So now let's just look at a few last examples of limits. So an important thing to remember when evaluating limits is look at the dominant term. And what I mean by this is basically look at the term with the highest power. So say we want to take the limit as x approaches infinity, and these are, looking at the dominant term for evaluating limits are most important when evaluating limits that will involve some sort of infinity. So if we look at this, well, let's say we have limit as x approaches infinity of x squared plus x over x cubed. The highest power on the top is 2, and the highest power on the bottom is 3. And infinity squared is going to be less than infinity cubed. Now, when first learning this, it can be very difficult to understand. But what you have to think about is, say you have some really big number, or let's say even just 100. 100 squared plus 100, so say 100 squared plus 100 over 100 cubed. Well, let's see, what's this going to be? We're going to have 10,100 over 100 cubed. Oh man, so that's going to be 1,000,000. One more 0. And as you can see, this denominator is much larger than that numerator. Now say we had 1,000, then this denominator would be even larger, much larger than the numerator. And as x approaches infinity, this denominator is going to get infinitely greater than the numerator, and therefore this is going to become 0. Now, what if we had some different terms? We'll still keep the limit as x approaches infinity, but let's say instead of x cubed on the bottom, we have limit as x approaches infinity of x squared plus x over 3x squared. When you have the same power on the top and the bottom, what you're going to do is you're going to take the ratio of their coefficients. So this has a coefficient of 1 and that has a coefficient of 3. So if the limit is approaching infinity, and you have an even power on top and bottom, the limit is going to be equal to the ratio of their coefficients. And you could look at this again intuitively. Say we have 100 squared plus 100 all over 3 times 100 squared. So we'll have the same thing. 10,100, and then on the bottom we are going to this time have 30,000. And this is pretty close to 1/3 right now, but as we increase x and make it greater and greater and greater, this term is going to become increasingly less important, and it's just going to focus on these terms, the highest power. That's why it's going to be a ratio of those highest power terms. And let's do one more with the same limit as x approaches infinity. Let's say it's x squared plus x over 3x. Well, here the dominant term is on the top, so similar to the first example with these, when the dominant power was on the bottom, we said that the bottom was going to end up being infinitely larger than the top. Well, now since we have the higher power on the top is going to be infinitely larger than the bottom. Therefore, we're going to have some infinity term divided by a much lesser term. So much larger infinity term divided by a much lesser infinity term. And that is going to be infinity, because the power on the top, the greatest power on the top is greater than the greatest power on the bottom. So that's about it with limits. And let's just look at continuity and the intermediate value theorem real quick, and that's it. So an important part of understanding continuity was before the 4 types of discontinuity, which we had already discussed. And another part that is very important is the intermediate value theorem, which I'll just abbreviate as IVT. So essentially what the intermediate value theorem states is, I'll give it to you in more technical terms and then explain it in a way that would make more sense. So we have a function f of x is continuous on an interval from a to b, including both. This is true if f of x takes on every value between f of a and f of b on this interval. Now you might look at this and be like, oh my gosh, what are they saying? It's actually pretty easy if you just draw a picture. So let's use the function f equals x squared again. F of x equals x squared. The parabola. Okay, let's see. Let's choose the points for our interval. Let's say 1, and then we'll take to 5. And we want to prove that somewhere between these numbers, f of x, or x squared, is going to be equal to 20. So we want to prove that somewhere here, f of x is going to be 20. And we can just look at this and say, okay, at 1, f of x is going to be x squared, so that's 1. At 5, x squared, 25. Well, look at this. This is continuous. This is continuous, so we can look at this point here. That didn't line up as I hoped it to. Move that over a little bit. Well, that point there, and then this point here, at some point in between, since this function is continuous, it is going to take on the value of f of x equals 20. Now, the intermediate value theorem does not say exactly where it takes on this value. It just says that it does take on this value at some point in the interval. So it's more abstract than giving a definite answer, but it is definitely very useful. So let's do one example of this. We'll say we want to verify that f of x equals 0 at some point on the interval 0 to 5, both inclusive, given that f of x equals x cubed minus 2x minus 2. All right. Well, here all we have to do, let's see. We want to find, let's first find f of 0, and then let's find f of 5. Well, f of 0, actually the first thing we should do here, let's make sure that this is continuous everywhere. All right, well, there's no denominator. This is not a fraction. There's no denominator that can equal 0. This doesn't have any points of discontinuity clearly. It's just a normal third degree graph. So since it's continuous, we can now take the next step and look at what f of 0 and f of 5 are equal to. And as long as f of 0, either f of 0 is less than 0 and f of 5 is greater than 0, or f of 0 is greater than 0 and f of 5 is less than 0, we can verify this statement. So let's look at f of 0. F of 0 is going to be, we plug in 0, 0, we get negative 2. Not the greatest 2. Alright, and f of 5, 5 cubed is 125, minus 2 times 5, that's 10, so that's 115, minus another 2 is going to be 113. So we have that f of 0 is going to be negative 2, and I will sketch this to the best of my ability. So f of 0 is negative 2, and f of 5 over here is 113. Well, since this is continuous, it's pretty clear that at some point this is going to have to cross over y, or f of x equals 0. Therefore, we can verify that f of x will equal 0 at some point in this interval. And the formal way to write this, with all these fancy math symbols and whatnot, is, we'll say for our answer, let me just, so separation there, so we'll say since f of x is continuous, f of 0 equals negative 2, f of 5 equals 113, f of 0 equals negative 2, and then f of 5 equals 113. The intermediate value theorem states that there is a C, so we're going to say C is a number, just like we were talking about before with the limits. And with the limits, it could also be an infinite number, but here we're just going to keep it to a finite number, so that there is a C that is an element of 0 to 5. So basically what this is saying is that there is an x value that is between 0 and 5, or in this interval. There's an x value in this interval such that f of x equals 0. And once again, we can say this. I'll draw the graph again real quick. F of 0 is negative 2. F of 5 is 113. We want to connect these 2 points. We have to go through f of x equals 0 somehow, because this is a continuous function. And that is just a quick recap of limits and continuity. And next time we'll get into the real calculus.